Hi, we're now going to look at a live case study. This is Malmberget in Sweden. This is a live case study. We currently monitor this site, and LKAB have kindly given us their permission to present this site. It's a pretty unique case study, and it's mainly looking at the effects of increased data. What benefits does more frequent data bring? But I'll also talk about the site in general as well. So here's the site. It's operated by LKAB. It's a high quality iron ore site. It's not too far from the Arctic Circle, 67.2 north, and it's a sub-level caving operation. So whilst this is highly automated and mechanized and efficient, it causes a lot of fast displacement, mainly on the hanging wall side of the caves. And so there is a constant transformation to move the local townspeople away from the subsidence zones. So it's a slightly different application for mining InSAR. One of the primary concerns is not one we're familiar with. And there are some special requirements. For instance, lateral displacement is very important, and the InSAR has to fit within this regulatory framework that the site has to adhere to. So we use 11-day TerraSAR-X as the primary source of data. You can see those footprints here in green and blue, the ascending, the satellites flying north and looking east, and for the descending, the blue, with the satellites flying south and looking west. But in addition to that, we also acquire data from ALOS-2 over the site, and this can be used as an independent check, but it really also helps to fill in the gaps that the vegetation creates for the X-band data. So ALOS-2 is L-band and much more resilient to the effects of vegetation. And because it's a seasonal site, we also use corn reflectors, which will retain high quality coverage for just the corn reflector points throughout the winter. At the site, we monitor using 3 different types of scatterer class. You may be familiar with persistent scatterers. These are points which dominate a resolution cell and persist over time. So they provide the highest quality observations or targets. In addition to that, we also monitor non-persistent scatterers. So these are also dominant, but they don't persist over the time. And you can see a time series here in the bottom of a broken time series that nevertheless contains useful information. And there are many non-persistent scatterers at this site, probably double the coverage by just including non-persistent scatterers. And then, as well as that, we use distributed scatterers. So these do not dominate the resolution cell. There isn't a giant boulder in the resolution cell. There is maybe grass, which nevertheless has enough consistency to provide useful measurements. You can see in the GIF, actually, the more sparse version is the persistent scatterers, and the more filled in version is the persistent and the non-persistent scatterers. And then many of these are also classed as distributed scatterers as well. So it's a seasonal site. We have snow on the ground for more than 6 months of the year. So over a 1-year period, all targets will be non-persistent in that sense. The idea of persistence is really about how long a period of time are you talking about. So over a year, obviously, we'll definitely get some snow. And the most challenging period of the year is the snow melt. In the spring, that is the period of most change, whereas the period of freezing just before the winter sets is there's less change going on there. And the effects of snow is usually to remove coherence. We can see on the right here, these are measurements. So don't forget that measurements are over some period. Interferograms are created over a period. And these are the shortest interferograms we can create at this site. And the longer and lighter the segment, then the more coherent this measurement was. So over this green period, this is the summer, this is when we have the highest coherence. But over the winter, you'll see that it's not a complete loss. Most sites with snow, for instance in Utah, would have no coherence in the winter. And we'd just basically pause the InSAR unless they had something like corner reflectors. But here, for whatever reason, probably because the snowpack is very dry, there is some coherence at some times. So we continue to monitor using standard InSAR throughout the year. So despite the fact that there's snow on the ground most of the year, you can see in this figure on the left, the white period here, that's the snow-free period. Despite that, we do get a reasonable amount of coverage throughout the year. So let's consider what happens if we add more data. As I said, our TerraSAR-X dataset is acquired on an 11-day frequency for each footprint. However, in between those passes that are 11 days apart, there is another satellite acquiring 4 days later. So you can acquire data on this 4747 repeat. You can form interferograms that are 4 days long and then 7 days long and 4 days long, because 4 plus 7 is 11. And this doubles the amount of data that you can receive. So shown in the top of this figure, this what TSX and PAS would acquire. So PAS is the name of the Spanish clone of TSX that is coherent with TSX. So this doubles our annual data from 66 images to 132 images. So many more points in our time series, potentially. But what other effects are there? We're making shorter measurements. Shorter measurements mean less displacement. And less displacement means easier unwrapping. So unwrapping is a key process that happens in InSAR. This is really how satellite InSAR circumvents the phase ambiguity issue that we have with ground radar. So ground radar, once you kind of measure you get to the end of your wavelength, you're done. You don't try and unwrap the data. But with satellite InSAR, because we're post-processing, we can perform unwrapping, which basically converts this red jagged sawtooth line into this blue line. We're trying to integrate these measurements, which when they reach their limit, they plummet back to zero. So we're just kind of resetting, undoing that limiting factor there. So this is it sounds, we're really just counting fringes. 1, 2, 3. I can count my fringes, multiply by my half wavelength and come up with some displacement. But it's usually a tougher operation than that. If we look at this interferogram here, this is a 4-day interferogram. Counting these fringes is already tougher than this. This is what an 11-day interferogram looks like. There are many more gaps. There are many more fringes. So in essence, what we're saying is if we have a simpler job with unwrapping, then our counting of these cycles will be better. And if our counting is better, then we will underestimate the displacement less. So that's the biggest danger, if you like, with not danger, the biggest issue with pour and wrapping is an underestimation of the displacement. It's pretty hard to overestimate the displacement. Another data set, before we look at the results, let's talk about a second data set that we have here. LiDAR was acquired in 2011, 2022, and these images show the difference between those two LiDAR scans that were 11 years apart. So in the data, you can see that there are these kinds of discontinuities, these abrupt changes, and LKAB have inspected some of these and found them to be fractures. So if we take this difference, we can draw on these lines. The white ones are confirmed fractures and the black ones are possible fractures. And later on, we're going to compare the InSAR data with these fractures to see how well we can recover this. Because if we have displacement, which is abruptly different, that should show up in the InSAR, we would hope. Okay, so what are our results? Here's our effect on coherence. Coherence here is on our y-axis and time is on our x-axis. And you can ignore the shape of the point here and really focus on the color, because the red points are TSX only and the black points are TSX with PAS. And we can see a general trend that the TSX plus PAS points do have higher coherence. And the reason that coherence is important, because really coherence is our measure of quality of the data. So if we have higher quality data, everything becomes easier. We can model signals easier, we can unwrap easier, and we should have lower noise in our results. Let's now look at the effect on coverage. So coverage is, of course, closely linked with coherence. If I have 15 measurable periods for a point, so 15 periods between images, because that, remember, is our measurement. It's the measurement between the images. The measurement is not the image itself. So considering these periods between images, if I, out of 15, get reasonable coherence for half of them, I could fit a rate to that. It wouldn't be a very good rate. I might have quite a bit of noise. I will probably end up with a reasonable amount of noise in the result as well at the end. But if I double my number of images, I now have 30 periods with which to fit data. And I have a much better chance of getting to a decent result with that much more redundancy. Our image here shows the difference in coverage between TerraSAR-X, TSX, and TSX plus PAS. On the left, the difference is in summer. So there are some differences, but it's not a huge amount. And on the right, we see that winter really benefits from this added PAS data. There's much more coverage when we add PAS. Let's now talk about displacement magnitude. So remember that shorter measurements have less displacement and are in turn easier to unwrap. So there's less chance of underestimation. We expect to be closer to the real value of displacement. In the top figure, we can see a red profile drawn, and This displacement here is the difference in displacement between TSX and TSX plus PAS. If we plot that profile for both of those displacement rates, we can see that the blue line, which is TSX plus PAS, is almost double that of the TSX alone in red. And the green on the bottom is the difference between the two. And I've marked 3 areas, A, B, and C, because these are inflection points in this transect. And they actually coincide with areas where the displacement changes. So this is where you are more likely to get a problem, more likely to get an unwrapping error, because the data is less able to characterize it if there's not enough, if the sampling can't keep up. In the TSX only, when we hit point A, the displacement actually goes down a little bit. So this is an unwrapping error, and it doesn't recover. That from that point we are separated by the blue line, and then once we get to B, that happens again, where it's unable to correctly resolve this change in displacement. There aren't enough samples. And then once we get to C again, there is another unwrapping error. So yeah, the blue line, TSX plus PAS, much better able to characterize these sudden changes in displacement activity. And then looking at a heat map of the area, we can overlay our cracks. On the left, we have the Terrace RX displacement rate, and on the right, we have Terrace RX with PAS. So you can still there are holes in both of these, but there are fewer holes on the right. So better coverage as expected. But also note that the TSX plus PAS is much more able to show these changes in displacement rate. So here there's a fracture line, and you can see in the InSAR that the heat map changes color there. And then at the top as well, these two fracture lines, these diagonal ones here, are much better characterized in the TSX plus PAS than they are in the TSX alone. So that's one means of kind of ground truth whether the quality of the results is indeed reflecting reality. And that's it. Thanks very much.